Hello, I'm Rachel Simantov. I'm in grade 9, and this is my innovation project where I build a framework for optimal pandemic management. Ever since 2020, as we all know, COVID has caused a lot of loss in society in terms of both lives lost and in terms of economic damage. In late 2020, a few pharmaceutical companies managed to create vaccines against COVID, and more recently, a few companies managed to create medication against COVID. Now, of course, this is great news in terms of finally gaining the upper hand against COVID, but we must still recognize that each of these medical preventatives come with monetary costs of their own. Furthermore, vaccines and medication may be deployed in varying methods. For example, 25% of the population may be vaccinated and all symptomatic COVID contractors may receive medication. Or 70% of the population may be vaccinated and no medication may be used. Now, one of these cases must be better for society in terms of the death toll and in terms of economic cost. But which case is it? And also, these are only two possibilities out of very many. Now, this prompts the question, is there a third case that is more cost-effective than any other deployment method of vaccine and medication? So the question in my project is, in order to minimize total societal loss, what percentage of the population should be vaccinated, and how should we deploy medication? Method. So first of all, the goal of the project is to find the optimal deployment method of vaccines and medication that minimizes the total loss to society. So the first thing we must do is assign a quantifiable definition to what total loss means. So the total loss is defined as the sum of the following components. We have the sum of life loss plus the cost of vaccinations, plus the cost of medication, plus the cost of any labor-related losses. So now that that's been established, how do I answer the question? Well, I used Python to code a computer simulation that reflects the way that COVID is spread amongst the society of Alberta. All right, procedure. First thing I did was I coded a simulation of the Albertan society. So I simulated a society of 4 million people who constantly walk sort of randomly. Next, I coded the population of viruses. So every virus is assigned two numbers between 1 and 100. The first number stands for its contagiousness, the second stands for its lethality. Now, the higher the number, the more contagious or the more lethal the virus is. And each virus can be represented on this graph. So for example, a virus can have the numbers 30 to 12, meaning that there is a 32% chance for the virus carrier to infect a healthy person and a 12% chance for the virus carrier to die. You can see that its placement in the graph represents these numbers pretty well. Now keep this graph in mind because we'll be getting back to it later. Okay, so as a healthy individual gets close to an infected individual, the following may occur. So the healthy individual may become infected. Now the probability of infection is dictated by the virus's contagious level. So for example, for a virus with the numbers, again, 30 to 12, there's a 32% chance that for the healthy individual to contract this virus. Now, if infection does occur, then the infected individual will carry a mutated virus that is close but not identical to the infecting virus. So for example, if the original virus's numbers are again 30 to 12, then the mutated virus's numbers may be 30, 15. You can see these numbers are close but not identical. Okay, so in the case that the individual is infected, the following may occur. The individual may die. Now again, the probability of death is dictated by the virus's lethality level. So, for example, for a virus with the numbers 30 to 12, the probability for the infected individual to die is 12%. In the case that death does not occur within 14 days, the individual will recover and cannot be infected by similar viruses for 5 months. So this is again represented in this graph. So the area highlighted in dark red is the area in which viruses can't infect the individual. Okay, so what we just discovered is a simulation of the pandemic's biology. Now, up until now, the simulation reflects the way viruses and humans interact. Right? We have a simulation of the virus population, the human society, infection, and immunity. But from here, the medical management of the pandemic begins. This is where the project becomes really interesting, and this is where the project's question is answered. So I'll repeat the question. In order to minimize the total societal loss, what percentage of the population should be vaccinated, and how should we deploy medication? Well, first of all, let's look at what vaccines and medication do. So being vaccinated decreases the chance of infection or contagiousness by 90%. So in this graph, the virus dot goes down from moderately contagious in the left picture to barely contagious in the right picture. Then being medicated decreases the chance of death or lethality by 50%. So again, you can see the left picture, the virus is moderately lethal. In the right picture with medication, it is barely lethal. In addition, medication also shortens the duration of the illness from 14 days to 9 days. Okay, so the simulation is run in batches. Every batch contains 100 simulation runs. This is done in order to achieve reliable results. Now, the difference between each batch is in the percentage of the society that is vaccinated and whether or not medication is provided to symptomatic COVID contractors. For example, in this batch, each of the 100 runs simulates a society in which 55% of the population is vaccinated and no medication is in use. So for each simulation run, the societal loss is calculated based on death toll, number of sick people, cost of vaccines, and cost of medication. So the loss that we outlined before. And for each batch of 100 simulation runs, the societal losses were averaged. The smallest value of total loss belongs to the most cost-effective method. So now that we've understood the method that I used to find the optimal way to deploy medication and vaccines, let's look at one run of the simulation and get a sense of what it looks like. This is analysis. So we start the simulation by infecting random individuals in the society with random viruses. Note that the dots representing viruses in this graph are scattered pretty evenly. Okay, so in the simulation, the individuals are represented by 4 colors. We have asymptomatic individuals, so people who do have COVID but don't show symptoms. These are green. Symptomatic people who are yellow, very sick people who are red, and healthy people who are blue. And we can see a reflection of these individuals on this pie chart, which visually represents what amount of the population is asymptomatic, symptomatic, and very ill. I did not include healthy people on this pie chart. Okay, so let's get back to this graph. In the beginning of the simulation, we saw that the dots on this graph were pretty evenly distributed. You can even rewind the video to see what this looked like. But now we can see that they've sort of converged into the top left corner. And we can also see that in this pie chart, most infection cases are actually asymptomatic. Why is this? It's because viruses that kill easily and are not contagious aren't able to survive natural selection because it's very difficult to transmit them from one person to another. Thus, their non-existent offspring are not able to be represented in the graph. On the other hand, viruses that don't kill and are very contagious are very, very easily able to survive natural selection because they are easily able to be transmitted from one person to another. And for this reason, their very many offspring are the ones who populate the graph the most. Alright, so the screen we just saw was one simulation for a specific predetermined rate of vaccines. Now, what we're really interested in order to answer this project's question, is the loss that is caused to society by the pandemic. We want to calculate the loss for the various rates of vaccines that may take place with and without applying medication. So in this screen, we can set the rates of vaccines and medication for 4 independent simulation runs, each of which come from a separate batch. So I ran this 100 times for every possible batch that we have, and the average loss for each batch can be seen in this table. The conclusion is very straightforward. As we can see in the table, the minimum societal loss is observed where 55% of the society is vaccinated and medication is used on symptomatic COVID contractors. The implication of my project on society is really immense. This framework that we have of modeling viruses biology, human biology, and a simulation of the combatants holds true for any infectious pandemic, not only for COVID. Furthermore, this framework can be very, very easily modified or expanded. For example, I modeled my viruses with only 2 attributes, which were contagiousness and lethality. We saw already that natural selection emerges from these 2 features alone, which reassures us that my simulation is already an accurate reflection of reality. But adding more attributes to viruses may give an even more accurate reflection of reality. Now, the same would hold true for the simulation of human society. So I implemented temporary immunity after recovery, but I did not model, for example, cohorts. State decision makers can use this framework to find the most cost-effective way to deploy medical combatants. This would save society billions of dollars, and the unused medical resources could be sent to countries where the resources are very much needed. So that concludes my innovation project. I want to thank all the judges who are judging my project, and of course, a really huge thank you to my family and to my teachers, people who've supported me. I hope you enjoyed this video and hopefully you learned something new. Thank you so much for watching.